Fins are a surprisingly common geometry for heat transfer. Think of opening up a desktop computer and looking in. You would find some objects that look like this, these devices known as heat sinks that enable you to remove heat from an object. The circuit board is the green part at the bottom here. On top of that is a component like a CPU. That CPU generates a lot of heat, and it would destroy itself if we didn't have some method by which that heat could be removed. That's what a heatsink is for, this object up top, which has a base and fins that come out of it. These fins create more surface area, and that surface area allows us to dump more heat to the environment. Rather than looking at a collection of many fins together, as we have here, we can instead look at just one fin first. This fin, shown here in gray, is on a base, which is the white object behind it. The fin is hottest at its base and gradually cools down as we go to the end of the fin. It has dimensions in L, T, and W. L is the length of the fin, T is the thickness, and W is the width. We're going to assume that the width of this fin is much, much greater than the thickness, and that the length of the fin is also much greater than the thickness. This will dramatically simplify the math. We can look at this same fin now from a side view. Here, we are emphasizing that the fin goes from x equals 0 to x equals L. It has a thermal conductivity of K. It has a temperature of T sub B at the base. And the air surrounding the fin has a temperature of T infinity in the bulk and a heat transfer coefficient of H. The heat current here is Q equals H times A times T minus T infinity. And the key effect of the fin is to increase this value of A so that we can create a larger heat current. The addition of the surface area, though, can of course change the temperature distribution, which is what we're interested in. To simplify the math, we want to assume that T is only a function of X. This requires that R double prime convection is much greater than R double prime conduction, that the resistivity due to convection is much greater than resistivity due to conduction. This means that 1 over H must be much greater than T over K. The reasoning behind this statement is that if the resistivity due to convection is much greater than that due to conduction, this means that there will not be that much of a temperature change along the thickness dimension, the Y dimension. And hence, we can treat this as a temperature distribution that exists only in the X direction. Here we are emphasizing conduction in the Y dimension along the thickness because most of the heat loss is along the faces of this fin that are defined by L and W. Getting heat to this face that is defined by L and W requires heat transfer in the Y dimension along the thickness dimension. We can implement a dimensionless group that reflects this condition, which we will call the Biot number. This criteria then can be written as Biot number equals resistivity due to conduction over resistivity due to convection. We plug in with the appropriate parameters, and we find the Biot number equals H times T over K. That is, the Biot number provides a ratio of the convective heat transfer away from a surface divided by the conductive heat transfer to that surface. This means that our assumption that T is a function of X alone requires that the Biot number is much, much less than 1. Typically, we'll set the cutoff at 0.1. Consider an aluminum fin, which is a millimeter thick, and that fin is transferring heat to convecting air around it. If we plug in the corresponding values of K and H in this dimension of 1 millimeter, we'll find a Biot number which is much, much less than 1. It's 0.00025. which means this assumption is valid and we can treat this temperature distribution as depending only on x, but it has no y dependence. Again, we're not worried about a z dependence here. This would be the dimension coming out of the page in the two-dimensional diagram drawn in the upper right-hand corner. This is because the majority of heat loss is through the faces defined by L and W, which is in the y dimension.